Isaac Newton was the first to make a systematic study of color. Passing sunlight through a glass prism, Newton showed that sunlight is composed of a mixture of all the colors of the rainbow. Newton called this spread of colors a spectrum, and noted that the colors were formed in the order red, orange, yellow, green, blue, and violet. Sunlight is an example of what's called white light. White light is a combination of all the colors. Under white light, white objects appear white, and colored objects appear in their individual colors. Newton showed that the colors in the spectrum were a property not of the prism, but of the white light itself. He recombined the colors with a second prism to produce white light again. In other words, all the colors, one atop the other, combine to produce white light. White is not a color, but a combination of all colors. Black is also not a color, but is the absence of light. Objects appear black when they absorb light of all visible frequencies. Even a polished surface may look black under some conditions. Highly polished razor blades stacked together and viewed end-on appear black. Light that gets between the closely spaced edges of the blades gets trapped and is absorbed after being reflected many times. Black objects that you can see do not absorb all the light that falls on them, for there is always some reflection at the surface. If not, you wouldn't be able to see them. The colors of most objects around you are due to the way the objects reflect light. The color of an opaque object is the color of the light it reflects. Different materials have different natural frequencies for absorbing and emitting radiation. At the resonant frequencies where the amplitudes of oscillations are large, light is absorbed. At frequencies below and above the resonant frequencies, light is re-emitted. If the material is transparent, the re-emitted light passes through it. If the material is opaque, the light passes back into the medium from which it came. This is reflection. Most materials absorb light of some frequencies and reflect the rest. If a material absorbs light of most visible frequencies and reflects red, for example, the material appears red. This square reflects all the colors illuminating it. In sunlight, it is white. When illuminated with a blue light, it is blue. This square absorbs all the colors illuminating it. In sunlight, it is warmer than the white square. The color of an object depends on the kind of light used. A candle flame is deficient in higher frequencies. It emits a yellowish light. Things look yellowish in candlelight. An incandescent lamp emits light of all visible frequencies, but is richer toward the lower frequencies, enhancing the reds. A fluorescent lamp is richer in the higher frequencies, so blues are enhanced when illuminated with fluorescent lamps. A red piece of glass appears red because it absorbs all the colors that compose white light except red, which it transmits. A blue piece of glass appears blue because it transmits primarily blue and absorbs the other colors that illuminate it. Blue glass only transmits energy of the frequency of blue light. Energy of the other frequencies is absorbed and warms the glass. The material in the glass that selectively absorbs colored light is known as a pigment. Electrons in the pigment atoms selectively absorb light of certain frequencies in the illuminating light. Other frequencies are re-emitted from atom to atom in the glass. Ordinary window glass is colorless because it transmits light of all visible frequencies equally well. White light from the sun is a composite of all visible frequencies. The brightness of solar frequencies is uneven. The lowest frequencies of sunlight in the red region are not as bright as those in the middle range yellow and green region. Humans evolved in the presence of sunlight, and we are most sensitive to yellow-green. The blue portion of sunlight is not as bright, and the violet portion is even less bright. The radiation curve of sunlight is a graph of brightness versus frequency. Sunlight is brightest in the yellow-green region. Because of our evolved sensitivity to yellow-green, we see it as the brightest color in the spectrum. Many fire engines are now painted yellow-green to make them easier to see at night.